So at this point, we've created our geometry. We have our engineering data defined. We're ready to go proceed with defining our model. So I double-clicked on Model, and that'll open up ANSYS Mechanical. We'll pause for a moment while that loads. Okay, here we are in ANSYS Mechanical. We have our geometry, and we have we've imported both the surface and the solid. And that surface has the unextruded hole there. Just to avoid any problems, let's go ahead and suppress that so that it will definitely not be included in our analysis. So we have our geometry. You can see that's a solid geometry. We have aluminum. Let's look at our solid and come down here to materials. So it's assigned structural steel. Let's go ahead and use, I'm going to select aluminum there. You saw we also could have assigned a new material or created a new material. In this case, we only have one body here, and so I don't need to make connections with the body. You could use connections to ground, but we'll do that with displacements. So let's come down to analysis settings. I want to set up our boundary conditions first. So in this case, we want to simulate a load, and I could do that. So I can put a force on there or a pressure. And when I do, I'm just going to go ahead and select force this time. And with a force, you could see that I could come up here and I could select a point. I could get a vertice. I could select a line. Select a line. Or I could select a whole area. And this area will be preferred because it'll average out that load over that area so that it'll start out a little more uniform. If in actuality I could select, say, a line, as long as it was far enough away from where I cared about, the stresses would spread out uniformly over a distance. But better to start out as close to the stress distribution as you want. So I select that surface, and I can hit apply. And now, rather than a vector, let's go ahead and choose components. And so I can see that the normal to that's in the x direction. And I'm just going to select 1,000 in the positive, in the x direction. This is going to default, or this doesn't matter exactly what magnitude I choose, because I'm going to be looking at a ratio of stresses as we go forward. All right, so I've got a force applied. Now, when we draw a model, we typically put forces on the other side, but that doesn't guarantee stability, right? If I have 1,000, and again, there's some rounding error, it gets a little bit unstable and it starts accelerating to infinity, which is a little inconvenient. And so instead, what we want to do is just apply a displacement boundary condition that would constrain it to be stable, so it'll have whatever reaction force is necessary. On this surface, so if we apply a load or support, let's apply a displacement. And again, I could pick a surface here, and if I could put, we definitely want our x to be 0, and now I could have, now if I just set x equal to 0, there's nothing to provide stability in the y and the z. Because this is a plane and it's not moving anywhere on that plane, that will prevent rotations, but it won't prevent a translation in the y or the z direction. So I need to constrain those directions as well. Now, I could come in here and put 0 in these directions, but that would prevent transverse shrinkage from the Poisson's effect. And so that would create an extra stress at these edges that wouldn't really be there in actuality. You know, if I'm a long ways away from where I care about, say I'm worried about the stresses by this hole, yes, I could do that, but it's not best practice. Instead, let's just go ahead and fix the 0 here, and we'll leave the others free. And let's add a separate displacement, and we can pick, I'm going to pick a vertice down here and go ahead and make that fixed in all dimensions. Now, that'll probably be fine here. It might be even better if, given the symmetry here, if we picked it on the surface. But this should be adequate for this case. If I see a high stress in there, then I would reconsider. So I have displacements. It's fully constrained in all degrees of freedom. I've applied a load. Oh, looks like I forgot to hit apply on my displacement here. So let's go ahead and reselect that and hit apply. I could see that because there was a question mark next to this displacement. Now I need to look at my mesh. And the mesh, as we talked about, is really important to the quality of the analysis that comes out. In this case, we really want to see that, and so we want to start, let's go ahead and let's just look and generate the mesh that it defaults to. Okay. So that is a really coarse mesh. You can see there's only one element through the thickness, and there's we've got some distortion around here. That's a pretty funny looking element that I'd have some concerns about. Not a good mesh. But we'll go ahead and start here and refine from there. So let's go to the solution and insert some of the cases we want. Let's go ahead and plot total deflection. We're going to want stresses. In this case, since I have stresses in the x, let's go ahead and do we'll go ahead and plot the von Mises stress, since we talked about the most relevance for ductile. And we'll keep it simple at that right now. And solve. Okay, and we see we have a plot here, and our sigma max is 12,466 psi. And you can see it's showing up right at these two nodes there, and the gradients are pretty uneven. This is clearly not a real good, accurate solution. So let's go look and see what we can do with the mesh. First, I want to show you, or if you come down here under statistics, I can see I have 849 nodes. So let's look at that as we go through. Now, one way to change the mesh is through global parameters. And so we can adjust our element size. It said the default was 0.2, so let's roughly cut that in half. So let's do 0.125. Enter, and let's look at the mesh that it generates. Okay. So now I'm 2 through the thickness, pretty orderly. It's gotten a little bit better in the middle. There's still some elements that would be of concern. I can look at my statistics, and now I have 4,357 nodes. So increased by roughly a factor of 5. Let's solve the stresses. Right now, the stresses were 12,700. Now it's only 15,923 psi. So you can see the answer changed with the level of mesh. So what we're going to do is going to repeat this. Let's have that mesh again. Enter, and then resolve. And we're going to do this until we reach a point where the change in stress is minimal. So now it's 15,553. I should mention in your lab, you're also going to look and see what the max deformation is. So you have 0.002104. Now let's look at the nodal statistics. So now I've got 24,510 nodes. And this looks like it's getting there, but I would just go ahead and do one more iteration and see if it's converged.